VSEPR. VSEPR stands for valence shell electron pair repulsion. That's what we're talking about today. We're going to talk about how molecules actually get their shapes and how we can determine those using line-wedge diagrams. By the end of this video, I'm hoping that you'll be able to use electron domains and the VSEPR rationale in order to determine any kind of molecular geometry of common chemicals. Additionally, by the end of this video, you'll have a nifty little cheat sheet to use and to study with in order to excel at any kind of VSEPR questions with line-wedge diagrams. Let's waddle right into this lesson. Through this video, I will be filling out a table format of the wonderful cheat sheet that's behind me. However, if you'd like a paper version of it that you can write in yourself and kind of have to use in your own tests and practice, you might want to get a printer paper and make it look like that. If you can make a piece of printer paper look like that, then you can fill it in as we go along in this video together. The table behind me is the same exact thing that I just showed you for the paper format of your cheat sheet, but I'm going to be filling it in here for all of our sanity's sake because I really can't draw that small on the paper and have you see it on the camera. We've been drawing a lot of Lewis dot diagrams, and we also recently learned that we can make those Lewis dot diagrams look like spherical 3D models of molecules. But how else do we know how a molecule is going to contort in space? How is it going to arrange the atoms on each individual molecule? What kind of angles are in between those atoms and why? This is where VSEPR comes into play. Now, if you're looking at your paper, you might notice that those molecules look flat. But in real life, molecules are not flat and far from it. In fact, molecules are so far from flat, as you have depicted on your paper, that if one single atom in a molecule is arranged in a different way, i.e. if one atom is pointing forward instead of backwards, this can cause a drastic change in how that chemical acts or reacts in its environment and what it's supposed to do. For example, in the 1950s, there was a drug called thalidomide. Thalidomide was used by pregnant women who had morning sickness, and it was supposed to help with that morning sickness. Now, there's only one single atom on the entire molecule that is facing outward instead of inward, or vice versa. So this is called R versus S in chemistry. It's basically whether or not there's an atom facing at you or if the atom's pointed away from you. Now, mind you, it's the same exact atom. It's still the same element. But the difference being is that it's facing at you or away from you. That 3D structure of it is what makes all the difference. Thalidomide caused severe birth defects in the 1950s to 1960s in women who took this morning sickness pill. And the reason for that is because the drug was really effective at getting rid of morning sickness. The trouble is that you couldn't just separate the molecule itself with the specific atom pointed in the correct direction. And once ingested, the opposite direction caused severe teratogenic birth defects. So there were babies that were literally born missing all of their limbs, their entire arms, their entire legs, just because this one atom was facing the wrong direction in 3D space. That's nuts. So no, molecules are not flat in real life. They are very much 3D. We just use the Lewis dot diagram in order to get to the 3D molecule, what it should look like. For example, the glucose above my head. You can see it's very much 3D, not flat. So if you've made your paper cheat sheet, go ahead and follow along and make the Lewis dot diagrams for the following chemicals in this order in your Lewis dot diagram column. Let's start with carbon dioxide. That's CO2. We're going to put the least electronegative atom in the center. There's one carbon, and there's dioxide, so there's two oxygens. Carbon has 4 valence electrons, 1, 2, 3, 4, and oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now we need to play connect all the lonely electrons. So here's one lonely one, there's another lonely one, here's a lonely one, and there's another lonely one. Of course, we're not going to leave it like that. That looks atrocious. We need to clean it up. Much better. Let's move on to boron trifluoride. Boron trifluoride has 1 boron atom and 3 fluorine atoms. Boron has 3 valence electrons and fluorine has 7. Now let's connect the lonely electrons. Perfect. Let's redraw that guy so it looks a lot cleaner. Next, we have sulfur dioxide. There's 1 sulfur and 2 oxygen atoms. Sulfur has a valence of 6 and oxygen has a valence of 6. Let's connect the lonely electrons. Uh-oh. Now remember, sulfur is one of the exceptions in our Lewis dot diagram, sulfur and phosphorus. We can break apart a lone electron pair in order for the bonding to occur. So we're going to break apart this pair here in order for us to bond. Now we can see that we actually have a lone pair on sulfur. Okay. Let's redraw this molecule to make it look cleaner. I've circled that lone pair for you on the central atom, i.e. sulfur, just so you remember it's there. Let's move on to methane. Methane is CH4, cow farts. That's 1 carbon, 4 hydrogens. Now carbon has 4 valence electrons and hydrogen each has 1. If we connect all those lonely electrons together, you see that we have 4 single bonds. Let's clean that up. Ammonia is next, and H3. That's 1 nitrogen, 3 hydrogens. Each hydrogen has 1 valence electron and nitrogen 5. Let's play connect the lonely electrons. And as you can see, we have a lone pair on the central atom of nitrogen and 3 single bonds. And I circled that lone pair on the nitrogen atom for you as well, just so you don't forget it's there. Moving on to water. Water is H2O. H has 1 valence electron and oxygen has 6. Connecting the lonely electrons. And let's clean it up. I've circled both lone pairs on the oxygen this time so that you don't forget they're both there. Let's move on to phosphorus pentachloride. Phosphorus pentachloride has 1 P and 5 Cls. I'm just going to draw this one bigger and we'll put the clean molecule in the box. Phosphorus has a valence of 5 and each chlorine has a valence of 7. Let's connect the lonely electrons. There's one, there's one, there's one. And remember that phosphorus is an exception and we can split apart the happy couple in order to make all these connections work. Let's clean that up. And last but certainly not least, we have sulfur hexafluoride. That's 1 sulfur and 6 fluorines. Sulfur has a valence of 6 and fluorine has a valence of 7. Let's connect all those lonely dots. One there, one there. We're gonna have to break this guy apart because sulfur is one of the exceptions where we can do that, and break this apart as well. Whew. All right, so we broke the exception on sulfur twice for this one. Let's clean this guy up. Whew. I know that's pretty tiny down there, but it's the same molecule just cleaned up now. So then how do we get this molecular shape? Remember that electrons are the whole reason why an atom has shape. It has an electron cloud. So the whole size and shape of an atom is dependent on the electrons that it has. It's not dependent on the nucleus because the nucleus is super tiny, super dense in the center of the atom and only accounts for the mass. It doesn't account for anything else. It doesn't dictate the size and shape of the atom. The electrons do that. So therefore, electrons determine the 3D shape. So essentially, everything about chemistry boils down to the electrons. Where are the electrons? How many electrons are there? And what are the electrons doing? And the way we depict this molecular shape is usually by a round sphere or a ball, and these individual atoms are each depicted by their atomic radius in terms of how big that sphere would be and how big their electron cloud would be. If we put many spheres together, then we have molecules or bonded molecules, and that shape itself of the overall molecule is dictated by the electrons that are close to each other, repelling each other, or the lone pairs that are also around individual atoms within the molecule. And how these electrons all interact with each other is what determines how that molecule is going to arrange itself, where all the atoms are happiest and the electrons are repelling but yet close to each other enough to all be happy and content. And this is where valence shell electron pair repulsion comes into play. Just like the name suggests, we're looking at the valence shell electrons, and if there are any pairs of electrons in the valence shell, we're looking how they repulse or how they repel other electrons nearby in order to make an entire molecular shape. So just as a blast from the past, remember that electrons are intrinsically negative. Therefore, if they are negative and you put 2 negative things next to each other, the orbitals repel each other like 2 negative magnets. You can't force them together. They're repelling each other. But the thing is that atoms have to bond together to fulfill their ultimate dream of being like the noble gases. They all want these octets. So they bond together to try and get their octets to be like noble gases, but that puts the electrons in a pretty precarious position because electrons don't want to be near each other. They're both negative. So since the atoms want to pair together, the electrons kind of have to cope with the fact that they want to pair together and still be together, but as far away as possible. So this turmoil, this push of the electrons that they have to deal with and cope with, determines the shape of the entire molecule. So the thing to keep in mind for the VSEPR models, when we're thinking about line-wedge diagrams and how to dissect how many electron domains there are and all that jazz, which we'll get to in a second, is that you always want to think that you are the central atom. Be the central atom. Be the center atom. So the arrangement of the valence electrons, or the bonding electrons, around the central atom is what determines the 3D shape. So if you are trying to determine this yourself, you need to pretend that you are the center of the universe, the center atom. So please keep in mind for the rest of this video, when I am deducing the electron domains and so on and so forth, I am always referring to it from the perspective of the central atom. I am pretending I am the center. So for example, from the central atom would be carbon in this methane molecule over there. And from the central atom's perspective, which is carbon, it would have 8 electrons total, and that would also be 4 areas of electrons. So it's not just the electrons individually, but also 4 general areas of electrons where there's bonding going on. That molecule there, its central atom would be N. N, we're looking at the electrons that are surrounding N. We are being N. And from N's perspective, there are 3 bonds and 1 lone pair. There are still 4 areas of electrons, but they're different kinds. There's 3 bonded pairs of electrons and 1 unbonded pair of electrons. Why does this matter? Let's move on and find out. The first definition we need to recognize in VSEPR, valence shell electron pair repulsion, is electron domain. Now, what is an electron domain? Think of a domain like your home, where you live. It's your domain. So an electron domain is where the electrons live. They're cute little homes. Electron domains are basically any group of electrons functioning as one unit, again around the central atom. We're thinking about it from the perspective of the central atom. Who gives a hoot about all the atoms that are connected to it? Just the central atom is all we care about. So electron domains include both the lone pairs of electrons and the bonding pairs of electrons. So when we're counting up or trying to figure out how many electron domains a central atom has, we're going to count up both the bonding and the lone pairs of electrons that surround it. So in this picture here, where you see M, M is the central atom that I want you to look at. So back over to this picture, if we're wanting to count up how many areas of electron domains there are, we're looking at both bonding and lone pairs. Notice that they have their own names. So if there happens to be 2 electron domains, like in the first one up top, notice there's 2 bonds on either side of M, regardless of what's attached to those bonds. We don't care. Remember, we only care about M. So from M's perspective, we have 2 areas of electrons. And so we would call that linear. If there are 3 areas of electrons, both bonding pairs and lone pairs, if there are any, this would be called trigonal planar. There's 4 electron domains, then we call that structure or that shape tetrahedral. If there are 5 areas of electron domains, we call that shape trigonal bipyramidal. If there are 6 areas of electron domains around our central atom M, then we call that octahedral. So for example, for electron domains, if we were going to look at NH3, which we had on a previous slide already, but now I have it as a Lewis dot diagram above my head, and remember I said there were 3 bonding pairs and 1 lone pair. For electron domains, for that name we're looking for, we're going to count up all of the electron domains present, whether they're bonding or lone pairs. And it's always looking from the central atom. So from N's perspective, N is the central atom in NH3. We have 3 bonding pairs, 1 lone pair. That gives us a total of 4 areas of electron domains. Now we already know that if there are 4 electron domain areas, we call that electron domain tetrahedral for 4 from the previous slide. So here, the 4 pairs of electrons that surround the N on ammonia would mean that the electron domain name for ammonia would be tetrahedral. Remember that electron domains account for both the bonding pairs and the non-bonding, those lone pairs that are around a central atom. Well, we did learn about double and triple bonds at some point, so how do those play into this electron domain geometry? How many do we count? Do we count both of the bonds, one of the bonds? In this case, when we're looking at double and triple bonds for the VSEPR model, the double bonds function as one unit. They kind of function as an apartment. They're stacked on top of each other, so we look at them as one unit or one domain. So for example, in the case of CO2, where there is a double bond on either side of the central atom C, carbon, in the picture over there, we can think of the double bond on either side of the carbon as a much fatter single bond. And that fatter single bond just means that there are still two electron domains around the carbon central atom. So there's still just two areas or two main localized areas where electrons are living. So in this case, this would be called linear because there's only two electron domains. This is the time where you can pause the video and see if you understand what we just talked about by filling in your own cheat sheet. So in the electron domains column of your little cheat sheet, write the number of electron groups surrounding the central atom for each molecule. So if you have CO2, we already went through that one, that's the first molecule on your paper, you know that there are two electron domains. So in the electron domains column next to CO2, you would write 2 because those two areas, those two double bonds account for only 2 electron domains. Go ahead and pause the video here and try and fill in the rest before I give you the answers. Now that we know what electron domains are, let's go back for our Lewis dot diagram molecules on our cheat sheet and put in the number of electron domains that should be for each group. For carbon dioxide, we're looking from the central atom's perspective of how many areas of electrons live around it. So for carbon, as the central atom in carbon dioxide, we can see that there are 2 areas of electron domains. So for carbon dioxide, we would write a 2 for our electron domains. For boron trifluoride, we're going to think about boron being the central atom. So from boron's perspective, how many electron domains does it have surrounding it? Hopefully you're seeing there's 1, 2, and 3. So in the electron domain box for boron trifluoride, we should write the number 3. How about sulfur dioxide? From sulfur's perspective, we need to think about the electron domains. How many areas are there electrons around sulfur? Hopefully you remember that the lone pair is included in the electron domain. So we have one area here, another here, remember a double bond counts as one area like an apartment, and another one here. So for sulfur dioxide, we have 3 areas around sulfur where electrons are living. How about for methane? Methane's central atom is carbon, and so from carbon's perspective, how many places are electrons living? We have 1, 2, 3, and 4. So the electron domain value for methane is 4. And moving on to ammonia. For ammonia, N is the central atom. So from nitrogen's perspective, let's check out and see how many areas of electrons live around N. We have 1, 2, 3, 4. The lone pair counts. Moving on to water. Oxygen is the central atom in water. So from oxygen's perspective, how many areas of electrons are living around it? 1, 2, 3, 4. How about phosphorus pentachloride? Phosphorus is the central atom in this molecule. So from phosphorus's perspective, how many areas are electrons living around it? 1, 2, 3, 4, 5. And finally, sulfur hexafluoride. Let's count how many areas are around the central atom of sulfur. 1, 2, 3, 4, 5, and 6. And there you have it, all of our electron domain values organized in our cheat sheet. So remember, we also have names for the electron domains. When there are 2 electron domains, we call that linear. When there are 3, we call it trigonal planar. When there are 4, we call it tetrahedral. When it's 5, we say trigonal bipyramidal. And when it's 6, we say octahedral. Now don't get caught up here. Molecular geometries are slightly different than electron domains. They use very similar names with a few exceptions. Some are quite different. This is literally the actual 3-dimensional arrangement of atoms in space and what we name them when they look like that. So these are the names of the full molecule that we give, all of the atoms connected to each other, what the final end product of the molecule looks like. So if a molecule looks kinked like a boomerang, that's a bent shape. So overall, that molecule looks bent. If the atoms are arranged in such a way where the molecule is literally straight across, that's why we call it linear. So molecular geometry has to do with the actual shape of the entire molecule, hence molecular geometry, once all the atoms are connected together. Let me show you what I mean by playing with this PhET simulator online that'll show you the difference of including lone pairs, not including lone pairs, and how we can see the name of the molecular geometry change based on the shape of that molecule because of the electrons and how the electrons are repelling each other, causing the shape to change in the first place. The link for the simulator is in the description below if you want to play with it yourself. I'm going to click down here in the bottom left-hand corner, molecular geometry and electron geometry. That's the electron domain. So for water, for this molecule of water that we're looking at here, I'm showing the lone pairs on oxygen. So this is H2O, and you can see I can drag around an H. I can kind of bully it to do what I want. But as I drag this and the bond gets closer to the lone pairs, you can see that they repel each other. They kind of bounce around like balloons off of each other. So these lone pairs at the top of our oxygen up here, they still have quite a bit of repulsion. They're not bonded to anything, but they cause the molecule to kind of shift depending on how close I can force those electrons together close to the bonds. Remember that there are 2 electrons in this bond here and 2 electrons in the other bond here, and they're all repelling. Notice that the electron geometry name is tetrahedral, meaning there are 4 areas or 4 electron domains. Just like we talked about, there's one here, and one here, and one here. So we do have 4 areas of electron domains. However, the molecular geometry, the shape of the entire molecule, looks like a boomerang. So we call this bent. The shape of what this looks like is bent. Let's check out another molecule, CO2. So the electron geometry is linear, and the molecular geometry is also linear. So if I bully CO2 by dragging the oxygens around wherever I want to, it compensates by becoming linear no matter how I drag it. How about NH3? NH3, we've been talking about that one a few times. So if we're looking at the electron geometry, we're trying to figure out from the central atom, that would be this blue guy, our N, how many electrons are around it. There's 1, 2, 3, 4 areas of electrons, 4 domains that electrons are living in. So the electron geometry is called tetrahedral. However, the molecular geometry is called trigonal pyramidal. If we arrange this guy to look kind of like this, you can see how it kind of looks like a pyramid. So what I'm getting at here is that the difference between the molecular geometry and the electron geometry has something to do with this lone pair up here. That lone pair each time is what's forcing this shape to look like this. If we didn't have this electron dense or negative region on top of N, if we didn't have this lone pair, then all of these bonds could go flat. So it could look like flat in the page, like this, but minus the lone pair. But because this lone pair is here, it's forcing these 3 bonds to be kind of pushed down instead of being able to lay flat. All right, so you might think, what about those names is special? You might have written them in order in the column on the cheat sheet, but how did I get those? Well, the reason I get those is that if I have a certain number of bonding pairs and a certain number of lone pairs, I will always end up with that molecular geometry name. So for linear to occur, I have to have 2 bonding pairs, no lone pairs. For trigonal planar to occur, I have 3 bonding pairs, no lone pairs. For bent, I always have 2 bonding pairs, 1 lone pair. For tetrahedral, I have 4 bonding pairs, no lone pairs. For trigonal pyramidal, I should have 3 bonding pairs, 1 lone pair. For bent, another bent, I have 2 bonding pairs, 2 lone pairs. For trigonal bipyramidal, I end up with 5 bonding pairs and no lone pairs, and octahedral is 6 bonding pairs and no lone pairs. This is the case for any molecule out there, so if you need to determine the molecular geometry name of any molecule you happen to bump into, as long as you can count up the bonded pairs and the lone pairs, you can determine the molecular geometry name. So when we're talking about molecular geometry, we really want to take into account where our lone pairs are at and how many lone pairs we have, because that's going to determine the overall shape. So back to this ammonia example where N was the central atom. We said there were 4 pairs of electrons around the end, so that gave it an electron domain of tetrahedral. However, there are only 3 electron pairs that are bonded, and there is 1 pair that's a lone pair. Because there are 3 bonded, 1 lone pair, it has a molecular geometry of trigonal pyramidal. All right, so for molecular geometry in our cheat sheet, we know that we have to consider both the bonding pairs and the lone pairs. So we kind of have to know how many we have of each. That's why I have 2 separate columns for each. So going back to our Lewis dot diagrams, we can figure out the number of bonded pairs and the number of lone pairs from the perspective of the central atom to then determine the molecular geometry name. For carbon dioxide, we have 2 areas of bonded electrons around our central atom of carbon. So in this case, the number of bonding pairs that we have for carbon are 2, and the number of lone pairs are none. We don't have any lone pairs on carbon. For boron trifluoride, from boron's perspective, we have 3 bonds around it. So we have 3 bonding pairs, and we have no lone pairs on boron. For sulfur dioxide, we have 2 areas of bonding electrons, and we have 1 area of a lone pair on our central atom of sulfur. For methane, the carbon is our central atom, and we have 4 areas of bonding pairs of electrons, and we have no lone pairs on our central atom. For ammonia, we have 3 areas where there's bonds, the bonds to the hydrogens, and we have 1 lone pair on our central atom of nitrogen. For water, oxygen is our central atom, and it has 2 bonds to hydrogen, and it also has 2 lone pairs. For phosphorus pentachloride, phosphorus is our central atom, and it has 5 bonds to chlorine, and it has no lone pairs on the phosphorus. For sulfahexafluoride, sulfur is our central atom, and it has 6 bonds to all those fluorine atoms, and it has no lone pairs on the sulfur itself. So let's go back and figure out the names for our molecular geometry according to the number of bonding pairs and the number of lone pairs of electrons. For the molecular geometry of carbon dioxide, we learned that if there were 2 areas of bonding pairs of electrons, that would be linear. Since boron trifluoride has 3 bonded pairs of electrons that can all be in the plane and no lone pairs of electrons to add extra repulsion to the other bonded pairs, it kind of ends up looking like a fidget spinner. So this one would be your trigonal planar. For sulfur dioxide, since there are 2 bonded pairs and 1 lone pair, we end up with a bent configuration for our molecular geometry. For methane, there are 4 areas of electrons around it and no lone pairs, so the molecular geometry is tetrahedral. With ammonia having 3 bonded pairs and 1 lone pair, we end up with a molecular geometry of trigonal pyramidal. Water is one of those weird ones where we also end up with the name bent for the molecular geometry because there are 2 bonded areas and 2 lone pairs. 5 bonded areas and no lone pairs, we end up with a molecular geometry of trigonal bipyramidal. And for sulfur hexafluoride, we have 6 bonded areas and no lone pairs, and that is a molecular geometry of octahedral. So the big takeaway here is that if you ever bump into another molecule, you can use these as your examples. So you can check out and see how many number of bonded pairs there are versus how many number of lone pairs there are. And if they match this same arrangement, then they'll have the same molecular geometry name for the chemical or for the molecule you happen to be looking at. So lines and wedges, think like this little box of images over here. And we've got wedges that are big, blocky, like black colored in triangles, and those represent something that's coming forwards, out at you. It's coming into your face. However, if you have a dashy line, that's kind of shaped like a triangle, that's something that's going away, behind you. So when you see the wedges, it's something coming at you. If you see dashy lines, it's going behind you. And anything that's a line, just a straight line, is in the plane. So it's flat in the plane. If you're going to draw a line-wedge projection, you have to follow a few basic steps. So step 1 is to arrange the model or the molecule itself in such a way that the maximum number of bonded electron pairs are in the same plane, i.e. they're flat in the plane. So like XY, think XY axes, so not Z, not coming out at you or away. You're thinking, okay, how can I maneuver this molecule so that the bonded atoms are going to be in the plane? The maximum number possible are going to be in the plane. Then from there, you'd move on to step 2, and say, okay, now that the maximum number are in the plane, how many electron pairs that are bonded to other atoms are coming towards you? That would be drawn with a wedge. And then how many are going away from you and which atoms are connected to it? That would be drawn with the dashy lines. If we were going to do the line-wedge projection ideology with a molecule of water, we're going to first try and arrange it so that the maximum number of electrons are in the plane, are flat. If I tried to do this with the molecule, you see that there's two lone pairs in the plane, but we're really wanting to focus on those bonded pairs because we want to draw the actual line, the straight line, to connect the atoms together when we're drawing line-wedge projections. So we're going to arrange this so that the maximum number of bonded electrons are in the plane, just like this. So we have H2O, we have its bonding electrons here, that would be a single line, and then we wouldn't need to draw a line wedge like the coming at you or going away from you for the lone pairs if we didn't want to. But really we're interested in the line wedge for atoms. We want to know where the atoms are in space. We don't necessarily care that this lone pair of electrons are coming out at us and that other pair of electrons are going away from us. We want to show where the atoms are in space. So let's show you one where the atoms can be arranged. Here's CH4, or methane. So C is in the middle, that's our central atom, and there are 4 hydrogens around it. If we're going to arrange this so that the maximum number of bonded electrons are in the plane, we're going to probably do this, and there we can see there's 2 in the plane, or you could just switch it around. You could go like this, and we can see that these 2 are in the plane. Either way is correct, it doesn't matter. But we can't get more than 2 in the plane, so those would be our straight lines. We would then also have one wedge with an H coming out at you, and one dashy line with the H going away from you. For the example column that we didn't go over together and left blank here, I'd love it if you'd go through that PhET simulator and draw out the sphere-looking model of each chemical. You can go through in the Real Chemicals tab and draw them in each box. So for example, the water had the sphere, sphere, slightly bigger sphere, and then we had the 2 bubbles with the lone pairs in them. That's kind of what you should have as an idea or a model of how it could look in 3D space as your examples. Once you have those examples drawn in, it'll be a lot easier to draw the line wedge shapes for each of these chemicals. But let's go through them together quickly. The line wedge shape for CO2 is still just a linear model. For boron trifluoride, its planar, kind of looks like a fidget spinner, and it's flat. For sulfur dioxide, we end up with a bent structure, so it looks like this. For methane, it's tetrahedral, so we end up with 2 of the H's in the plane, and 1 of the H's coming out at us, drawn with a wedge, and 1 of the H's going away, drawn with the dashes. Ammonia ends up having a hydrogen in the plane and the lone pair in the plane, while having a hydrogen coming out at you and a hydrogen going away from you. Water is drawn with both of the H's in the plane, and our lone pairs are the ones that are going away or towards you. Anytime we have a trigonal bipyramidal molecule like phosphorus pentachloride, we end up with 3 of the bonds in the plane, 1 coming out at us and 1 going away. So we would have 3 in the plane, like this, chlorine, 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 and then 1 of the chlorines coming out at us, drawn with a wedge, and the other chlorine going away from us with a dash. And for sulfur hexafluoride, whenever we have something that's octahedral, we end up with 4 of the atoms in the plane, 1 of the atoms coming out at us with a wedge, and 1 of the atoms drawn away, going away from us. So how do we know where to draw the atoms relative to each other once we have all this information? We have the electron domain names, we have the molecular geometry names. Now, how do we actually put it all together and draw a molecule based off of all that information that's correct, that's chemically correct? we have these things called VSEPR bond angles, and the angles are due to those electron repulsions between the non-bonded and bonded pairs of electrons around the central atom. So depending on how many lone pairs there are, depending on how many bonded pairs there are, determines the overall shape of the molecule, as we found in the molecular geometries. And now, once we know the molecular geometry, we also know the value of the bond angles between separate atoms. So for example, in this picture here of ammonia, you can see that A is our nitrogen, B is our hydrogens. We know that the A has a little lone pair on top, and because ammonia has this shape, the trigonal pyramidal shape that we talked about, we also know that the bond angle between the B atoms, our hydrogen atoms, on ammonia is 109.5 degrees. Why is this important? This is important for a lot of chemical syntheses. If we need to know how a chemical is going to interact with another one and how to create new chemicals, how to create drugs, chemical syntheses in general needs to know these bond angles between atoms to know how they will react with each other. So on your cheat sheet, there's a column that's titled bond angle. I would appreciate it if you just wrote from top to bottom exactly as I have it listed over there. So you'd have linear, 180 degrees, 120, 120, 109.5. Trigonal pyramidal is going to have that 109.5 degrees, 109.5 degrees again, 120 degrees and 90 degrees, and octahedral will have 90 degrees between all the atoms present. Please make sure that you have those bond angles written down in order. We're also going to fill them into our column here so I can show you what it would look like. Now these are where the bond angles come in really handy. This angle right here is 180 degrees. The angle between these fluorines is 120. The angle between these oxygens on sulfur dioxide is also 120. For the molecules with electron domains of 4 or tetrahedral, we always end up with 109.5 degrees between the bonded atoms. So here we have 109.5 degrees. Here we have 109.5 degrees. And here we have 109.5 degrees. For trigonal bipyramidal molecules, we end up with two different kinds of angles. We have a 90-degree angle, and we also have a 120-degree angle present. For octahedral molecules, we end up with 90 degrees between each atom present. Be sure to write these bond angles in on your bond angle column. So that's what your finished cheat sheet should look like. So the whole point we're learning this is because the shape is everything for a molecule. Once we know where the electrons are, we can determine the shape. And then once we know the shape of a molecule, we can determine its polarity. Once we know the polarity of a molecule, we can determine how it's going to react in its environment and with what. It's going to tell us its physical properties. If it's soluble, if it's volatile, any of those things we learned about in our MSDS lesson, this is how we know it. We know it from the molecule's shape determined by the electrons around the central atom. Therefore, in a roundabout way, VSEPR, valence shell electron pair repulsion, determines the physical properties of all the chemicals on the planet. So for example, if water was linear, if it was straight across like CO2, it wouldn't be a good solvent. We wouldn't be able to use it for cleaning and all the other applications we use water for. It also wouldn't freeze the same. So the fact that in winter, when ponds freeze, only the top freezes and the bottom of the pond stays liquid so that all the fish and plants don't die every winter is a property of the fact that water happens to be bent. So if water was linear, we would be screwed, essentially. Think of CO2. CO2 is linear and it's a gas. That means that if water was linear too, it would also be a gas. That means that all life on Earth would cease to exist because we wouldn't have oceans, lakes, or anything, and we would not be able to live without water. So keep in mind that water is not a linear molecule, ever. It's bent. And it's bent due to the fact that there are two lone pairs on oxygen repelling the two bonded pairs connected to hydrogen, causing an overall net dipole moment straight up because oxygen has a polarity region of slight negativity, whereas the hydrogens here have an area of slight positivity, and that causes this bent overall shape. Here's your first practice problem. Try to draw the Lewis diagram for nitrogen trifluoride. Figure out the number of electron groups, the name of the electron domain, and the name of the molecular geometry. Then try and draw the line wedge with the angles, using your cheat sheet as a guide. Go ahead and pause the video here and give this one a try. Your second practice problem is CH2Cl2. Draw the Lewis dot diagram for this one, number of electron groups, name of electron domain, name of molecular geometry, and the line wedge with the angles, the bond angles we talked about, between the atoms present, using your cheat sheet as a guide. Go ahead and pause the video here and give this one a try. If you'd like the answers to these two practice questions, please comment below and I will be happy to upload a video explaining how to do both of these and check your own answers, see if you got it right. And if you weren't practiced out enough already, here's some extra practice for you. For each of the 8 molecules that I have listed over there, be sure to draw the Lewis dot diagram, figure out the total electron domain numbers and the name that goes with those electron domains, the number of lone pairs, then the name of the molecular geometry, remember that does not include the lone pairs for the naming, and then draw the line wedge diagram using your atomic symbols, i.e. use Se and Cl to symbolize those atoms. If you're really looking for a challenge, give those bottom 2 a try, and you'll get some bonus ducks if you're able to get those. If you'd like the answers for these practice questions, please comment below and I'll be happy to upload a video giving you all the answers for these practice questions. I hope that helps you understand valence shell electron pair repulsion a little bit better, or VSEPR as we endearingly name it. Be sure to like this video, and for more educational content on chemistry help for all of those struggling with chemistry out there, please subscribe to my channel. Have a ducky day.
No ducks, no glory.